Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Physics Honours students. We have now the lecture on wave optics, especially the section on interference, and is the lecture number 17. And in this lecture, the contents are change of phase due to reflection, colors of thin films, conditions for constructive and destructive interferences, interference in thin films, and the conditions for bright and dark bands. And in the last lecture, I was telling you about colors of thin films. What do you mean by a thin film? A thin film is a layer of oil or petrol that is lying on the surface of water, that has been dropped on the surface of water. While you walk on the road, you see some oil or petrol being found on the surface of water, and when the white light is incident, when sunlight is incident, then you see the colors, and that is the reason why it is called colors produced by thin films. Colors produced by a thin layer of oil or petrol. A thin film means a film or a thin layer of petrol or oil. Then white light is incident on that. That gives to different colors, as I showed in the last lecture also. That coloration is due to the phenomenon of interference, because the common man may not be knowing why the region appears to be colored. The region appears to be colored because of the phenomenon of the interference. Now let us see from a scientific point of view how you get colors. When light is incident on, this is the thin film, right? This is the thin film. It is equivalent to the layer of the thickness of layer of oil or petrol. The thickness of the oil or petrol vapor is D. Okay. Then light is incident on the upper surface of the oil, getting reflected, as I told you in the last lecture. Partly it is getting reflected on the top surface. The remaining portion undergoes refraction, right? It undergoes refraction. It enters into the film or the oil and gets reflected at the bottom surface of the oil film at the point B. It gets reflected, and again, because it is coming from a denser medium like oil, water, you know, the refractive is 1.33. So you got oil here, so which is denser than air. Then the light ray comes here, and again when the light is entering from a denser medium to a rarer medium, it will be again getting refracted. So the refracted beam comes here. So the two light rays reflected from the top surface, I have written here reflected light coming from the surface, top surface at the point A, from the point B, from point C. Actually, the two light rays which are reflected, they interfere the depending upon the condition for constructive interference, if the two beams interfere, and depending upon the condition, either there will be constructive interference or destructive interference. What do you mean by condition? The condition that we have been talking about is, we have been talking about path difference. The path difference should be equal to integral multiple of lambda. That is the condition for constructive interference. If the path difference between the two light rays is equal to lambda by 2, 2n or 3 lambda by 2. In general, 2n plus 1 into lambda by 2. Either lambda by 2 or 3 lambda by 2, 5 lambda by 2 in terms of half integers. That is a condition for destructive interference. That means leading to darkness. The earlier one leads to a bright band. Now, what is path difference? Look at this diagram again. Light is incident on a thin film, demonstrates the optical path length difference. What is the path length difference or a path difference? This light ray goes getting reflected, right? From A it goes to D and so on. Whereas this light ray travels through an extra path, AB plus BC, right? The points D and C, there is no difference, right? From C you draw a perpendicular, right? From C draw a perpendicular, that is the point D, right? After D and C, there is no path difference, right? There are two parallel rays. You got two parallel rays from the point D and C, there is absolutely nothing in there. But whereas when you compare this light ray and this light ray, the second light ray undergoes an additional path AB plus BC, right? Not in air, but in a medium whose refractive index will be mu. Mu is 1 in the case of air, but here let us have in general the refractive index N2, or mu is the refractive index of the medium that you have got here, the oil film through which the light ray passes. How much the extra distance travelled by light ray in the medium 2, that is AB plus BC, right? AB plus BC. Then afterwards there is no path difference. Therefore, the path difference between the two light rays is nothing but the distance travelled, namely AB plus BC, in the medium which has got a refractive index. That should be borne in mind. That medium will come in the picture. I will show how do you calculate a path difference, right? And again, the light rays, there is a phase change. When do you get a phase change? When light ray is incident on a denser medium, from a rarer medium, light ray is incident on a denser medium getting reflected. When this reflection occurs, there will be a phase change of pi, or that a phase change of pi will be equal to a path difference lambda by 2. So, the two factors which are to be taken into account here are the extra distance travelled by the second light ray, namely AB plus BC in oil. That means you should take into account the refractive index also. The second point is when a light ray is incident from a rarer medium incident on a denser medium. Here there will be a phase change of pi. When a light ray is incident from a rarer medium into a denser medium, there will be a phase change of pi. That point also should be taken into account. Now, taking into account these 2 points, we will be calculating the path difference, and this path difference will be equal to n lambda or 2n plus 1 into lambda by 2, depending upon either you get n lambda or 2n plus 1 into lambda by 2, you will be getting a bright line or a dark line. So, the degree of constructive or destructive interference between the two light waves is dependent on the difference in their phase or path difference, right? The difference in development is dependent upon the thickness of the film layer, that is your D, the refractive index of the film that I told you, and the angle of incidence of the original wave on the film. Additionally, as I told you, a phase difference or a phase shift of 180 degree should be taken into account, or 180 degree or radiance may be introduced upon reflection at a boundary depending upon the refractive indices of the materials on either side of the boundary. So, a thin film is a layer of material with thickness in the sub-nanometer to micron range. that is oil film. As light strikes the surface of the film, it is either transmitted or reflected at the upper surface. At the upper surface, light ray will be getting reflected, partially it will undergo reflection and partially that will be transmitted. The light that is transmitted reaches the bottom surface of the film and once again it will be reflected. Consider a film of thickness T and index of refraction N. Let us assume that the light rays travel in air or nearly normal to the surface of the film. The light reflected from the upper and lower surfaces will be interfering. As I told you, the two light rays which are reflected from the upper surface and the light ray getting reflected from the lower surface that is coming here, these two will be interfering depending upon the interference that is taking place between the two light rays. There will be constructive or destructive interference and the colors will be appeared. The phase shift occurs if the refractive index of the medium the light is travelling through is less than the refractive index of the material is striking. That means, as I told you, if light is incident from air and is falling on glass, then there will be phase change of pi. Is that right? Or a path difference of lambda by 2. A phase difference of 2 pi, as I told you in the last lecture, corresponds to a path difference of lambda. The light is travelling from material 1 to the material 2, then a phase shift will occur upon reflection. The pattern of light that results from this interference can appear either as a light or dark band or as colorful bands depending upon the source of incident light. Now consider a transparent film of thickness T with refractive index mu. Let AB be the upper surface of the film and CD the lower surface. Let us look at the diagram. Right? This is the upper surface and the thickness of the film is T. AB is the upper surface, CD is the lower surface. Okay. This looks to be complicated, but it is not at all complicated. What happens is you have got a light ray here incident on the oil layer or petrol vapor. You have got a thin layer, right? This is a layer of thickness T having a refractive index mu, and the light ray which is incident on the upper surface gets reflected, then partially it undergoes refraction and getting reflected by the bottom surface, then comes here and again it will undergo refraction, and these two rays R and V, right, NR and UV, they will be interfering with each other. So you have to calculate the path difference, right? The path difference is QS plus SU. That is quite right. You can have QS plus SU itself if it is in air, but this takes place in a medium of refractive index mu. That should be taken into consideration. The other is the light ray is incident here getting reflected at the surface of a denser medium, then a phase change of pi, that should also be taken into account. Therefore, taking into account these two factors, so let me, for the sake of continuity, let me read. Some part of the incident beam is reflected by the upper surface along QR, okay. Then the remaining portion of the light is transmitted through the film along QS, okay. Then it will be getting reflected and then again undergo refraction. That is, so thus this transmitted beam undergoes reflection by the lower surface of the film. CD, SU is the reflected beam and ST is the transmitted beam from the interface CD. Where are SU and ST? Let us go back. SU you have got here, and ST, let us not worry about ST. SU is the beam that is coming here. Now these are the two beams which are of significance for our discussion. The ray SU undergoes reflection at the interface. Okay, SU undergoes refraction at a point B. UV is the transmitted beam and UW is the reflected beam from the interface. Consider the rays PQ or ray 1 and PQSUV as a ray 2. Ray 2 has travelled a greater distance compared to ray 1. Let me now show you PQR and PQSUV. What is PQR? PQR, this is a light ray, PQSUV, this is the second light ray. The point is, you have to remember the two light rays. The light ray getting reflected by the top surface, light ray getting reflected by the bottom surface. One is PQR, the other is PQSUV. Okay, these two light rays are interfering. Let us have a break at this point and come back at a break. Welcome back at the break, and we are discussing the phenomenon of interference when light is incident on a thin film. By thin film, what I mean is a layer of oil or petrol. So this is a layer of that you got a thickness of T, you got a layer of petrol vapor, petrol. So the light that is incident on the upper surface getting reflected, then partially is getting transmitted, coming here, going along this direction. Now these two light rays are important. So the paths taken by the two light rays are PQR, the one light ray, that is ray 1, the other light ray is PQSUV. That is what I have been telling you before the break. So the two light rays that we are talking about, light ray 1, PQR, the light ray reflected by the top surface, this is the light ray which is passing through the film, getting reflected by the bottom surface and coming out. These two rays, ray 1 and ray 2, are interfering, and the path difference between the ray 1 and ray 2 are to be calculated. The path difference between the two rays can be determined by drawing a perpendicular from point U to the line QR. UN is the normal to the line QR drawn from the point Q. You see here, you draw a perpendicular from the point U to QR, you obtain N. As I told you, from N and U, after N as well as U, there is no path difference. The path difference is only QS plus SU, that the additional path travel when compared to this light ray, what is that is happening? You have QNR, right? Here, so QN is the distance travel by the light ray 1. By the time QN, the light ray comes to N, this light ray passes through QS plus SU in the medium and comes to U. Therefore, QN as well as QS plus SU, that is the light travel by the second ray in the medium mu, these two are to be taken into account. So you have here the, as I told you, QN comes here. QN is the distance traveled by light ray 1 in air. So the reason why I am not multiplying by mu, because air refracted is 1. So QN is the distance traveled by light ray 1 in air. So that will be QN. Whereas for the light ray 2, QS plus U, that is light ray travelling in a medium which has the refractive index mu, that should be taken into account. So I multiply QS plus SU by mu. So therefore, the path difference between the two rays is given by the expression x is equal to mu times QS plus U minus QN, QN multiplied by mu. Mu in the case of air is 1. So QN into 1. Let R be the angle of refraction. Consider the triangle QSM. Where is your QSM? From QSM, you have to get QS in terms of T, cos R, everything. So let us look at QSM. You have got QSM, right? So from, look at this triangle, and what is cos R? SM divided by QS, right? SM divided by QS is your cos R. So QS will be SM divided by cos R, obviously, and your SM is nothing but thickness of the oil film, that is your T by cos R. Okay, QS will be T by cos R, and QS then equal distance, right? QS is the distance and the light ray is reflected, SU and QS will be equal, right? Obviously, QS and SU will be equal. The angles are R. So, QS, you have got expression now. The same expression will be added because your SU is here, QS plus SU multiplied by mu. So, QS will be T by cos R. SU will also be T by cos R. So, SU will be T by cos R. So, 2T by cos R. So, you got QS plus SU will be T by cos R plus T by cos R. It will be 2T by cos R multiplied by mu, right? From triangle QSM, you can find out sin R will be QM by QS. QM will be QS multiplied by sin R. So, QU will be equal to 2QM, that will be 2QS into sin R. So, that will be 2T by cos R into sin R. So, these are some of the things which can see from the trigonometry of the the triangles that you have got here. These are some of the things which can be easily understood. Therefore, consider the triangle QUN, sin I will be QN by QU. So, your QN will be QU multiplied with sin I. From the above equation, you can get QN to be equal to 2T into sin I multiplied with sin R by cos R. The Snell's law shows, what is Snell's law? The sine of the angle of incidence by sine of the angle of refraction will be equal to the refractive index of the material. The refractive index is defined as sin I by sin R, where I is the angle of incidence and R is the angle of refraction. Therefore, sin I will be equal to mu sin R. So, your sin I that you have got here will be equal to mu times sin R. From the equation that you got here, Qn can be rewritten as you replace your sin I as by mu sin R. So, your Qn will be 2T sin I multiplied with sin R by cos R. Okay. So, from the above equation we get x is equal to mu times 2T by cos R minus mu times 2T by cos R into sin square R. So, pulling out mu t 2T by cos R outside, that will be 1 minus sin square R. 1 minus sin square R will be cos square R. Cos square R divided by cos R will be equal to cos R, right? Cos square R by cos R will be equal to cos R. Therefore, what is x? X is the path difference between the two light rays. One light ray getting reflected and the top surface. One light ray being reflected by the oil layer or the oil film, the bottom surface of the oil film, right? That is the second light ray. We are trying to calculate, or we have calculated the path difference between the two light rays. That becomes equal to 2 mu t cos R. Okay, that is important relation. Then again, we have to take into consideration the phase change. The ray QR is a reflected ray and the ray UV is a transmitted ray. Okay, due to reflection, as I told you, there will be a phase change due to reflection. Whenever light ray is incident from a rarer medium into a denser medium, from air into glass or from air into oil, there will be a phase difference of pi or a path difference of lambda by 2. So, due to dissimilar reflection, because reflection is taking place from a rarer medium, when light ray is trying to go from a rarer medium into denser medium, there will be a phase change of pi or a path difference of lambda by 2. That, as I told you, should be taken into consideration. Therefore, along with 2 mu t cos R, this also should be taken into consideration. So, due to reflection, there is a phase change of pi degree or an additional path difference of lambda by 2 that should be introduced. So, the total path difference is written as x is equal to, what is x? Is the total path difference. That is, x is equal to 2 mu t cos R minus lambda by 2. Then what should you do? Having calculated the path difference, you know very well if the path difference is integral multiple of lambda, that is the condition for constructive interference. On the other hand, if the path difference is 2n plus 1 into lambda by 2 or lambda by 2 or 3 lambda by 2, then that is condition for destructive interference. Therefore, we have to equate this. right? Whether this becomes equal to get the condition for a bright fringe, the path difference should be equated to integral multiple of lambda. So, this path difference that we have calculated 2 mu t cos r minus lambda by 2, that is equated to n lambda, that is the condition for a bright fringe. Or in other words, taking lambda by 2 to the right hand side, you get 2 mu t cos r as 2n plus 1 by 2 into lambda. That is the condition for obtaining a bright fringe. Then we will see that the condition for bright fringe. We will go to the condition for dark fringe. The condition for the dark fringe, I think I am showing the diagram once again so that you should know where is your T. The refractive index mu comes here. The two light rays, one light ray is going in this direction, the other light ray is going in this direction. Then Qn is the extra distance travelled by first light ray. The Qs plus Su is the additional path travelled by the second light ray, but not in the air, but in a medium. This undergoes a phase change of pi because it is trying to be incident on a denser medium for a rarer medium. All these factors are taken into account. And then the condition for brightness I showed you earlier. Similarly, the condition for darkness, what is the condition for brightness? 2 mu t cos r should be equal to 2n plus 1 into lambda by 2. Similarly, the condition for dark fringe is 2 mu t cos r should be equal to n lambda. Same thing I am having here, that is equated to 2n minus 1 into lambda by 2. That becomes equal to 2 mu t cos r equal to n lambda. Above equations give the conditions for bright and dark fringes produced by thin films due to interference of light. What is meant by the interference between the two light beams? Where are the two light beams? You have one light ray which is incident along PQ on the top surface of the oil film. It is getting reflected and travels along the direction QR. In this process, it goes through a distance Qn. Remember, the distance Qn that is travelled by the first light ray, it is in air. On the other hand, when you go to the second light ray, it travels through a distance Qs plus Su, that is additional distance. After U and N, there is no path difference, right? Obviously, these two, the distances covered by light ray from N afterwards, and similarly from the point U, after point U, that they travel through the same distance. So, up to N and U, you have to find out what are the extra distances travelled by the two light rays. The first light ray goes through a distance Qn, whereas second light ray, because it goes through the medium of refractive index mu, travels through a distance Qs plus Su in a medium of a definite refractive index and then comes back. Therefore, you have to take into account the two factors. And again, another factor that I told you is, as far as this light ray 1 is concerned, it is incident in air and is falling on the layer AB, the top surface AB, an oil film. The oil film has got a higher refractive index. So, the light ray is incident from a rarer medium to a denser medium. That will lead to a phase change of pi or a path difference of lambda by 2. As I told you, these things are to be taken into account. So, when you look at the condition for a dark fringe, you get the expression 2 mu t cos r minus lambda by 2. In the earlier case, for a bright fringe, it should be equated to n lambda. For a dark fringe, it should be calculated, it should be equated to 2n minus 1 into lambda by 2. That turns out to be, because lambda by 2 can be taken to the right hand side, then what happens is your 2 mu t cos r becomes equal to n lambda. That is a condition for getting a dark fringe. Whereas the condition for getting a bright fringe, as I told you earlier, 2 mu t cos r will be equal to 2n plus 1 into lambda by 2. Okay, that is the condition for getting a bright fringe. What are mu? T, etc. Mu is the refractive index of the oil film or oil. T is the thickness of the oil film, and the cos R is nothing but the angle of reflection of the second light ray at the bottom surface. This is angle R. Okay. And now the summary of the today's lecture, they go as follows. There is a phase change when light ray is incident on a denser medium by angle pi or a positive difference lambda by 2. Colors of thin films arise due to constructive and destructive interferences, and the conditions for bright and dark fringes have been obtained, and these things will be made use of in the lectures to come. The questions are: what do you understand by colors of thin films? Question number 2, explain the path difference of light rays passing through the thin film. Give the conditions for constructive and destructive interference of light passing through thin film. With this, we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.